Hello everyone. Um, in this video, we are going to give you some example on Biot-Savart law. And in the last video, we have learned that if you have a little column segment here, if you have a little conducting segment, and if you run a current into this little metal segment, then you are going to produce a magnetic field at some observation point A. And this observation point doesn't have to be right about the metal center. It can be a distant. It can be at a distance A away from this metal center. And in this case, the conductive segment is in the direction of X. Uh, by Biot-Savart's law, you are going to end up with a magnetic field dB, delta B, which is equals to bracket Ui divided by 4 pi, and then times uh, delta L times sine theta. Sine, sine theta, where theta is the angle between vector A and the horizontal axis. And finally, the whole expression is going to divide A squared. A squared is the magnitude uh, of this length here, square of the magnitude of this length. So today we are going to um, use this formula to analyze uh, another experimental setup. And instead of having just a delta L, we are going to have a long length of wire. And this wire running from minus infinity to plus infinity. So this is your wire. And you are going to have the wire running from negative infinity to plus infinity. And we are going to have shown A is about at this position here, and the height of A is assumed to be H. And let's assume this point 0. 0 means is the origin. Now we are going to find the total magnetic field because of the current running along this wire. So instead of calculating dB only, we are going to calculate B due to the current running along this wire. And this wire has an infinity long, and is going to run from minus infinity to plus infinity. So this is the, the element of the question. So in other words, right, we are going to investigate uh, the magnetic field due to a long wire. So I better write this down here. The title of this video is going to be uh, magnetic field due to a long current carrying wire. current clearing line. So this is the title of the video. So now we are going to find out this magnetic field. Now, first of all, you have dB, right? This value here. So we are going to write down the formula again. dB is equals to mu I divided by 4 pi. And then sine theta. I'm going to write sine theta first, and then dr divided by a squared. And now uh, let's assume the length here is L. The length here is L. And according to what is presented in this whiteboard here, the length A should be equal to square root of L squared plus H squared because of the Pythagoras theorem. And we also know that sine theta is going to be equal to H divided by square root of L squared plus H squared. This length divided by the length A. So now we are going to substitute these two values into the original formula. So we are going to get mu I 4 pi, and then times sine theta. Sine theta is equal to H L squared plus X squared, and is a square root value. And then A squared. A squared is this one, which is very clean. L squared plus this one. And then do not forget the delta L. So now you have basically follow, you have all the information for this question now. But now, can we simplify this expression? I think the answer is yes. What we can do is replace this one with L squared plus H squared and to the power B divided by 2. So what is the value of the magnetic field? So B will be equal to 2 uh, um, integration of dB. And uh, what is what is this integral? Yeah, according to this equation here, you can do that. Or I can just simplify this straight away. Simplify. I can just do the simplification on the fly. So I'm not going to going through all the stuff. Instead, I just jump a little bit, and perhaps the H can be moved to here as well. So what I got here is dl L squared plus H squared B divided by 2. And uh, the integral will run from minus infinity to 0. and we have to multiply the magnetic field contribution due to uh, the left half and the right half of this metal, of this conductor. So the whole expression will be multiplied by 2. And if you do it very carefully, uh, if you do it very carefully using the integration table, then eventually you will find the answer. You will be surprised. Uh, the answer is going to be mu I divided by uh, divided by 2 pi h. So basically, the end result is going to be exactly the same as that obtained using Ampere law. If you use Ampere law, then you will obtain, say, magnetic field at the observation point A. And in this case, I am going to assume the observation point A is h away from, is this much distance away from the conducting wire. And if you use the Ampere law, you are going to get exactly the same way. Uh, so this is the beauty of the Biot-Savart law. Thank you.